So our next speaker is Morgan Saidel from Caltech, who's going to tell us about a survey of atmospheric escape around gas giants.
Oh, yeah, that is not the title slide, though.
Let's go there.
Okay.
Okay?
Yeah, I think that's it.
So the time's there. Perfect, take it away.
Okay. All right, so hi guys. I'm Morgan Saidel. I'm a fourth-year graduate student here at Caltech. Can you guys hear me okay? Okay, awesome. And so yeah, I'm going to be discussing some initial results from the first mass loss survey of gas giants orbiting F-stars. So we've heard a lot about atmospheric escape so far. Just to kind of ground us in the specific type of atmospheric escape we care about for the study, what we care about are hydrodynamic outflows. These occur when you have a planet on a close-in orbit around its host star, meaning it's undergoing long and intense periods of radiation from that star. And that radiation, in particular high-energy X-ray and extreme UV radiation, will enter the atmosphere of that planet, ionize it, and provide energy in the form of heat to lift the bulk portion of the atmosphere out of the gravitational well of the planet, allowing it to escape. And that's what creates these hydrodynamic outflows that we care about. And so we've heard a lot today about how we can actually detect these outflows. And one of the most successful ways we can detect them is using metastable helium. As mentioned previously, metastable helium absorbs a 1083 nanometer photon, and it's this absorption that we can actually use to detect escaping atmospheres. So just to illustrate how we do this is a photometric survey, so I kind of want to give a schematic here showing what we're going to be looking for. As a planet transits in front of its host star, we see a dip in brightness if we measure this in some reference bandpass like TESS, which is optical. Now, if that planet's atmosphere is escaping, then the hydrogen and helium and metastable helium that make up that atmosphere will be present and absorbing at a large distance from the planet. Meaning if you were to observe the transit of that planet in a bandpass that's sensitive to that absorption, like the absorption of a 1083 nanometer photon by metastable helium, you should see an increase in the transit depth or an excess absorption. And it's these excess absorptions that we can use to infer the presence of an escaping atmosphere. This technique has been widely successful so far. To illustrate this, I have a plot here showing confirmed exoplanets as white circles as a function of planet mass and Jupiter masses on the vertical axis, and then orbital period in days on the horizontal axis. And the different colored circles you see here correspond to robust detections of atmospheric escape using metastable helium. Not pictured here are Lyman alpha detections. There are about 5 of these. They're not as many as helium, so I'm not going to talk about them today. And so the main takeaway here is that overwhelmingly, there are a lot of orange circles on this plot. And what that means is that overwhelmingly, our measurements of mass loss are for planets orbiting cooler stars like K-stars. And that means the information content that's informing our mass loss models and our general understanding of atmospheric escape is shaped by our observations of these cool systems. And theoretically, we wouldn't expect that to be a problem. We'd expect atmospheric escape to behave the same on planets orbiting hotter or cooler stars. But I'm starting to potentially doubt that. And the reason that I have those doubts is actually these 2 blue points right here. Those represent the first detections of atmospheric escape on planets orbiting hotter F-stars. These happened about a year and a half ago. And they seem to paint a vastly different picture of atmospheric escape. To illustrate this, I have a 3D model here showing a typical outflow on a planet orbiting a K-star. So for reference, the star is in the middle, the planet's on the left. The shading is the log of the gas density. And while this isn't true for all planets with outflows orbiting K-stars, many of them, like WASP-107 and WASP-69, have their atmospheric escape confined to these tails that trail the planet's orbit. And so this can result in escape rates as fast as about 10 to the 10 to 10 to the 11 grams per second. Now, for the first 2 detections of atmospheric escape on planets orbiting these hotter F-stars, we see a completely different picture. We see these very spatially extended outflows. For reference, HAPP-32b, one of the systems there's a detection for, its outflow extends up to 53 times the planet radius. And HAPP-67b, the other system for which there is a detection, its outflow extends up to 130 times the planet radius. So these outflows are incredibly spatially extended. Not only that, they're also very fast. They're up to 100 times faster than the fastest outflows we see on planets orbiting K-stars. So this is really cool, but also a little bit puzzling. Why are some of the fastest, by orders of magnitude, and most spatially extended outflows occurring on planets orbiting F-stars? Is it that these 2 detections are anomalies? Or perhaps do outflows categorically behave differently on planets orbiting hotter stars? That's the question I wanted to answer. And I think to answer that question, what we have to do is look at what these two systems have in common. Do these commonalities result in anomalously large detections that we see here? Or did these commonalities potentially apply to all gas giants orbiting F-stars, in which case we'd expect to see these large inflated outflows across the board? Okay, so what are some of these commonalities? The first is that both systems have host stars with relatively fast stellar rotation rates. Their stellar rotational velocities are both above 20 kilometers per second. Why does that matter? Well, in kind of the simplest picture, in order to get a more massive, bigger outflow, you need more power for the outflow, which would be more XUV radiation. F-stars aren't known to be super XUV luminous, but we know from great studies like Johnson et al. 2021 that if you have a fast rotating star, it can be more XUV luminous, or at least more XUV luminous for longer. So perhaps these large outflows are driven in part by the fact that the host stars are moderately rapid rotators. I think in this case, then we'd expect other gas giants that orbit similarly fast rotating F-stars to then have inflated outflows if this is the true culprit. And so this is a testable idea. Another commonality shared between these two systems is that both planets fill a large fraction of the Roche lobe with the planet radius alone. Meaning, if you put an atmosphere on top of that planet radius, it's very likely that these systems are undergoing Roche lobe overflow. That can create massive outflows. If that's really the source that's driving these inflated outflows, then we'd expect other gas giants orbiting F-stars that also fill a large fraction of the Roche lobe with the planet radius alone to also have similarly inflated outflows. So again, another testable idea. And lastly, another commonality, this is kind of our everything box, is that these two planets both orbit F-stars. And most of our mass loss models and understanding of atmospheric escape is heavily parameterized for our observations of planets orbiting cooler stars. And that means that there could be additional energy sources and heating and cooling that we're not accounting for in the radiative transfer in those models that could apply to these systems. Things like NUV-driven photoevaporation or bomber escape could be driving large outflows across the board. So again, we'd expect this process to be intrinsic for maybe all gas giants orbiting F-stars. We'd expect to see large outflows kind of across our sample. Okay, so how do we figure out which, if any of these factors, could be contributing to the large outflows we see on HAPI-32b and HAPI-67b, and whether or not these large outflows are anomalous or apply to all gas giants orbiting F-stars? Well, you can test these factors by setting up an observational survey, which is exactly what we did. We wanted to look at atmospheric escape for gas giants orbiting F-stars, and we decided to do this with Palomar Observatory. Palomar has the Wide Field Infrared Camera, or WIRC, which is equipped with an ultra-narrowband filter that's centered on that 1083 nanometer metastable helium line. The filter is actually shown here. And so that effectively allows us to perform metastable helium transits, which is awesome. Okay, so what are our survey targets? I'm showing our survey targets here in blue. And basically, in order to detect atmospheric escape, you need to make sure that your systems will actually have detectable excess absorptions. You don't want to stare at something that you don't have enough signal to noise to detect an outflow. So that means what we essentially had to do is model outflows for our systems ahead of time. We did this with 1D EUV-driven photoevaporation models. Those can be a bit problematic. I'm not going to go into the details of that. Happy to talk about that later. Basically, just note that the point size here is proportional to their signal to noise or their outflow strength or mass loss rate. And for reference, I'm showing HAPI-32b and HAPI-67b here, the two systems with the detection. They're not part of our survey, although I would like them to be. Okay, so ultimately, what we want to know is whether or not our outflows are bigger or stronger than the predictions here. And that's because on HAPI-32b and HAPI-67b, we're seeing that their measured outflows are much larger than the EUV-driven predictions. Again, we're seeing outflows that are larger than we typically see on EUV-driven photoevaporative planets orbiting cool stars. And so we want to know why these large outflows are occurring. And one of the ways we can determine that is if we see similarly inflated outflows in patterns indicative of a source. For instance, if Roche lobe overflow is truly the source creating these inflated outflows, then we'd expect other planets orbiting that already fill a large fraction of their Roche lobe with the planet radius alone that orbit F-stars to also have inflated outflows. If other factors like high stellar rotational velocity are what is driving the large outflows here, well, then we'd expect other gas giants orbiting similarly fast rotating F-stars to then also have inflated outflows. And lastly, if there's some other energy source that we don't yet understand that's a property of these F-stars, well, then we'd expect across the board to have large inflated outflows, if that's a property that's intrinsic to F-stars and the gas giants that orbit them. Okay, so what do we actually see? I have some initial results to show you. That's why this is called initial results. We unfortunately have been weathered out 8 out of 18 nights at Palomar, which is almost half. Trials and tribulations of being a ground-based observer. But what you're looking at here are 3 tentative detections of atmospheric escape. It's 1 observation per planet. The black data points are our bin data points. The blue line is the best fit model to the transits, but it's fixed to the transit depth of TESS, so it's like a reference line. And the red line is the best fit model to our data. And again, these are metastable helium transits. And so what we're seeing are, again, these tentative detections of excess absorption, a bit stronger for WASP 180, a bit weaker for the other 2 systems. That's still interesting because we're not seeing super strong outflows. Okay, so what does this all mean in the context of the large outflows on HAT-P32b and HAT-P67b? To answer this question, I'm going back to our survey plot here. The red circles are the measured signal to noise. You can see they're very comparable to the EUV-driven predictions for our survey targets. So what does this all mean? Well, first, we're not seeing inflated outflows in our survey. And I think what that's telling us is that the large outflows on HAT-P32b and HAT-P67b seem to be more unique to these systems than we initially anticipated. And I don't think we can really say what is driving these outflows right now. We don't see similarly inflated outflows in any pattern like Roche lobe overflow or high V sin I that can indicate a driver. And so I think it's a little upsetting to not know what the driver is, but we were still able to answer one of the survey's main questions, which is whether or not these large outflows are anomalous. And I do think they seem to be anomalies. They don't seem to be broadly representative of the outflows that we're seeing on other gas giants orbiting F-stars. However, in the future, we'd like to finish up the survey, weather permitting. It should be done by the end of February. Maybe as we continue to study more planets, we will get a better understanding for what's going on. Additionally, we'd like to work on 3D models for this system and for our survey targets in general to better understand the interaction between the star and the planet at the outflow launch site. And lastly, as we've heard a lot, this is a Know Thy Star, Know Thy Planet conference. What we don't know is the stellar XUV spectra for any of these targets, and the stellar XUV flux is directly powering those outflows. So we're in the dark about the power for the outflow. If we can get that information, I think that's the missing puzzle piece to really answer what's going on. And that's it. Thank you.
Thank you very much. Questions? Yes, we have one over there, and then we'll go here as well.
This is super interesting results. With the transit method, right, it's a differential measurement, and some of these outflows can have massive tails that go on for hours.
Yeah.
Is it possible that instead of probing like a baseline level of no helium versus you are seeing helium, that you're just comparing the massive tails and you're not actually seeing the full depth discrepancy?
Yes, that is entirely possible. Actually, I prepared a backup slide for a question like this, just in case. So there's a great paper by Suresh Visapragada who looked at TOI 1420b. So that's the Palomar measurement on the left. That's a 3D model made to match the excess absorption that they see. And you can see that there's definitely a tail that leads and trails the planet. But when they take the number density of helium and they actually extrapolate that with the helium transmission function, they get something like this in the bottom right that shows that most of the absorption is actually during mid-transit. So we're not missing a lot, but there is some excess absorption that we might be missing before and after. But I do think that what we need is longer baseline because, like you're saying, you know, if you have this excess absorption that's continuing for hours outside of the transit, which is happening for HAT-P32b and HAT-P67b, it's a 12-hour total absorption. It's crazy for like a 3-hour transit. We could be missing that. We could be fitting our models to baseline that is still part of the extended absorption. The problem with the ground-based observing is we're limited in how many hours we can observe these targets, things like hour angle limits with Palomar as well. We are working to try and get back-to-back night observations for some targets, which should be happening in 2 weeks, weather permitting, so hopefully that will address some of your questions. But yeah, no, it's definitely an issue that we are dealing with. Great question.
Hey Morgan, nice talk. Since this is Know Thy Star, the F-dwarfs probably have very different magnetic properties. If they're past the Kraft break than stars with convective envelopes. What might that do to the stellar wind and then the interaction between the stellar wind and the planet, and if you had to speculate?
Yeah, no, that's a great question. I think that's something we can play around with more in 3D models. I would expect, depending on the strength of the stellar wind, to see more confinement. So I think Jess showed this earlier in her plots, or in her slides. As you increase the stellar wind strength, you're gonna get more confinement of that outflow. So I think that if the stellar wind is in any way shaping the outflows on any of these systems, it's probably weaker for HAP P32 and HAP P67, where we see these almost torus-like structures. Because we don't see any tail-like structures in our detections, I can't really speculate what's going on there in terms of stellar wind strength, but it definitely should have an effect, and we're hoping with additional observations and also some Keck data that should be coming in this summer that we can maybe better tell what's going on. But that's a great question and an important fact that we have to take care of.
Okay, we're going to have to leave it there, but more questions coming from Morgan in the Great. Let's thank her again.